All right, let's jump right in. Welcome to the Explainer. Today we're looking at something that is literally invisible to the naked eye, yet it holds the power to absolutely destroy an electric vehicle's motor drive system in just a fraction of a second. We are talking about calibration data errors. You see, in the world of high-performance EV dual-motor systems, if the highly sensitive calibration and baseline data stored in the memory gets corrupted, lost, or just written incorrectly, the consequences are, well, they're catastrophic. So today we're exploring a literal fortress of functional safety, figuring out exactly how automotive engineers build an impenetrable shield around this data to hit the incredibly strict ASIL D safety standard.
Picture this for a second. What actually happens when an EV motor completely forgets its own physical parameters? If even a microscopic data error happens, the motor's control algorithms start getting fed a distorted version of reality. Suddenly, instead of a nice smooth acceleration, the system might command massive negative torque, or it might draw a sudden violent overcurrent. And this isn't just a software glitch you can reboot from. This physically destroys the power modules. Preventing this exact scenario is the ultimate ASIL D safety goal. We absolutely have to guarantee that the fundamental physical data, things like resolvers, zero-point offsets, and current sensor gains, is perfectly preserved no matter what environment the car is in.
So, here's our roadmap for this explainer. We'll start with the anatomy of root causes, move into software and hardware co-diagnostics, check out the DFMEA prevention controls, then the PFMEA process controls, and finally wrap up with the DVP&R ultimate validation.
All right, kicking things off with Section 1, Anatomy of Root Causes.
Let's actually break down the physics of how this fails, step by step. First up is high heat. When you have extreme temperature swings hitting up to 125 degrees Celsius, the silicon dioxide insulation in the hardware actually degrades. The trapped electrons inside the flash memory's floating gate literally leak out through thermal emission. Second, you got radiation. High-energy neutrons from the atmosphere or even alpha particles emitting right from the chip packaging itself can strike the memory. And third, low-voltage sags. Imagine the system is trying to learn its 0 point, writing that data to the flash memory, and suddenly, boom, a massive power draw drops the voltage from 12 volts down to 6. What you get is called a torn write. It's essentially a half-finished, totally corrupted file.
Think about how wild and invisible this threat actually is. An SCU, which stands for Single Event Upset, is quite literally just a bit flip. A single invisible ionizing particle strikes the RAM cache and generates just enough transient charge to flip a bit from a 0 to a 1. Just like that, in a split second, physically baseless and super dangerous calibration values get loaded right into the motor's control algorithm. It is a completely random hardware failure from outer space or local radiation, and the system absolutely has to be prepared to handle it.
Now, it's not just microscopic physics from space. We have to look at the macro level too. Let's contrast those invisible environmental threats with real-world, human-sized process errors. Say a technician is replacing motor hardware during a repair, but they completely forget to run the motor commutation calibration. The software is now trying to use the physical 0-point offset of the old motor to drive the new motor. This mismatch generates a massive, dangerous D-axis parasitic current, which leads straight to severe overheating and runaway currents.
Which brings us to Section 2, Software and Hardware Co-Diagnostics.
So how do we fight back? With some seriously layered active defenses. First, right at startup, the system runs a dual-sector mirror built-in self-test. It reads the primary data alongside a backup mirror, verifying everything against a complex 32-bit mathematical signature. If the primary memory is corrupted, but that mirror is safe, it just overwrites and heals the primary on the spot. Then, while the car is actually running, a RAM background check is constantly hunting in the background for those random radiation bit flips we just talked about. And finally, plausibility checks. The system actively measures the current sensors at 0. If the physical reality of the hardware doesn't match the stored memory by more than 50 milliamps, it instantly knows the data is compromised.
Okay, so what happens when the system actually catches a fault? Well, it triggers a very strict ASIL D fallback strategy. If it happens to be a non-critical error, say a corrupted thermal cooling table, the system will just swap to default safe values and limit torque. That allows you to safely limp home at under 40 kilometers per hour. But if a critical resolver offset gets corrupted, the system does not mess around. It aggressively and instantly forces an active open circuit, safely cutting power to prevent the motor from mechanically exploding and logging a permanent diagnostic code.
I really want to highlight this number right here, 60 milliseconds. That's it. That is the fault-tolerant time interval, meaning it's the absolute maximum survival window the system has. From the exact microsecond an alpha particle flips a bit, or a voltage sag corrupts a sensor read, the vehicle's computer has exactly 60 milliseconds to detect the anomaly, diagnose the threat, and trigger that active open-circuit shutdown before the motor destroys itself. Moving on to Section 3, DFMEA Prevention Controls. This is where we get into how the system is physically armored up during the design phase. The DFMEA interventions here are honestly fascinating. Engineers use hardware error-correcting code memory that automatically fixes single-bit errors on the fly. The memory itself is physically locked into read-only, isolated zones by a protection unit, meaning stray, glitching code literally can't overwrite it. Then you have software algorithms leveling the wear across the flash memory to guarantee at least 100,000 physical write cycles. And my favorite part, strict physical keyways limit dynamic runout to less than 0.05 millimeters. This mechanically stops the rotor from ever drifting from its 0 point just because of heavy vibration.
You also have to deal with insane electrical noise. High-voltage silicon carbide switches operate insanely fast, and they can generate electrical transients of 10 kilovolts per microsecond. That kind of harsh electrical noise could easily scramble the SRAM data right as it's being read. So to block this, engineers build in specialized isolation transceivers with massive transient immunity. It basically acts as a thick, impenetrable electrical firewall around the memory.
Let's step onto the factory floor for Section 4. PFMEA process controls.
Out on the assembly line, the Manufacturing Execution System, or MES, is basically an unforgiving bouncer. The test machines run an automatic zero-point calibration, and if that math fails for any reason, the MES physically locks out the unit. It won't print the barcode, the defective unit physically cannot leave the line. The current sensors are also adaptively calibrated under very precise 10, 50, and 100 amp loads at the end of the line. And to top it off, every single byte of data is read back from the controller and mathematically verified against a master database using a heavy-duty SHA-256 encryption check.
And the physical strictness here is next level. Every single control board is subjected to 100% 3D X-ray inspection. They are hunting for microscopic air pockets inside the solder joints. The total voiding rate has to be 5% or less, and not a single void can exceed 1%. Why are they so obsessed with 1%? Because physical thermal fatigue over years of driving can cause those tiny voids to crack. If they crack, it instantly ruins the sensor impedance and completely destroys the precision calibration we just worked so hard to protect.
Finally, the last stop. Section 5. DVPNR, Ultimate Validation.
This is the proving ground, the absolute torture tests before these systems ever see mass production. First, they shake the system violently while slamming the temperature from -40 all the way to 125 degrees Celsius for 1,000 cycles. The memory has to retain perfectly, 0-bit loss. Second is the brownout test. While actively writing data to the flash, they instantly choke the power from 12 volts down to 6 for 20 milliseconds. The system has to use its auxiliary power to successfully finish the write with no torn files. And lastly, they run the motor at a screaming 12,000 RPM on a test rig and intentionally inject a bit flip into the memory. The system must catch it, shut down within our 60 millisecond window, and clamp any torque ripple below 5 Newton meters.
Now, pulling all this off isn't just lucky guesswork. Engineering teams actually use dynamic Python simulation models, just like the one detailed in today's source material. These tools precisely quantify those critical voltage boundaries and the thermal safety margins of the flash memory based on operating temperatures and capacitor degradation. It gives hardware teams exactly the data they need to perfectly tune their write cycle limits and debounce algorithms long before the metal is ever cut.
We've seen how incredible these defense mechanisms are today, from hardware ECC memory to software redundancy, all the way down to literally 3D X-raying solder joints. But as we wrap up this explainer, it leaves us with a pretty important question. Looking at your own engineering designs, or even just the vehicles you rely on every single day, are your system's parameters actually safely locked down? Or are you literally just one invisible alpha particle away from a 60 millisecond catastrophic failure? Something to think about. Thanks for joining me on this deep dive into functional safety.